have here Matthias Hammer. Matthias Hammer is coming to visit the CBPF now under the PCI program. He finished his PhD with Professor Carsten Hansen. Carsten is not here right now today, but he was around. He had to go home. And the Carsten is now has been hired by CBPF in the last competition. And Matthias is coming to do the postdoc here to go on with the work with Carsten. So Matthias is now coming for 2 months. Probably next year you'll come for a longer period. So he's going to speak about phenomenology of SUSY, and he told me that he's available to teach to those who are interested. Some technicalities he knows very well about the computation of final diagrams using special packages. So I think it's an opportunity for some of our people to learn this starting from activities. Okay? So Matthias, thank you so much for accepting our invitation for the talk. And okay, you have 1 hour, 15 minutes, 1 hour to give your talk, and we can ask questions afterwards.
Yeah, thanks for the nice introduction. Yeah, we'll talk about constraining supersymmetry in high energy physics. This talk will be at a very basic level, so we'll give a very brief introduction to the models that we have. So SUSY models in experimental high energy physics, like the MSSM, and we have the PMSSM, the CMSSM. I will always also very briefly cover other models. Then I have a section about tools for SUSY analysis, like spectrum calculators, EK calculators, and also cross-section calculators, with some examples of how the input and the output for these programs looks like. Then I talk about observables that we have that are sensitive to supersymmetry, so observables that we can use to discover or to measure supersymmetry. And finally, in the final part of the talk, I will very briefly cover global fits of supersymmetric models. So putting everything together in the Fitino framework, and I will briefly talk about the interpretation of the results that we get from Fitino. So let me start with an overview of the standard model in particle physics that we have. I assume you all know the standard model of elementary particle physics. So basically we know 6 different flavors of quarks, 6 different flavors of leptons, the 4 force carriers, and the recently discovered Higgs particle. And the standard model is described by this Lagrangian here, which has 19 parameters in total. And if we introduce supersymmetry to the standard model, basically all that we do is introduce one symmetry operation, which turns bosons into fermions and fermions into bosons. The generators of the symmetry transformation behave like spinors, so they have fermion operator, which means that they obey anti-commutation relations, like here. And a very important part about these generators is that they commute with the 4 momentum vector. So basically, if you impose a supersymmetric transformation on the standard model, you do not alternate the masses of the particles in the standard model. Come back to this point very shortly. So what happens to the standard model if we impose supersymmetry? Usually for the phenomenological considerations that we make, we consider exactly one supersymmetry transformation. We could think about imposing more SUSY transformations, but typically for the phenomenology that we have, we assume exactly one supersymmetry, which is referred to as n equals 1 supersymmetry. And this means that each degree of freedom in the standard model gets exactly 1 superpartner. So it's not really about the particles, it's about the degrees of freedom in the standard model that we have. And each of these degrees of freedom gets 1 superpartner. If we consider unbroken supersymmetry, or the perfect case, this would mean that the superpartners have exactly the same mass as the respective standard model particles. So the superpartner of the upquark would have the same mass as the upquark in the standard model, and so on. And then it is sometimes also useful to introduce an additional quantum number, which is called R parity, and it is defined in a way that it is +1 for all the particles that we know in the standard model, and -1 for all the additional superpartners that we get via the supersymmetry transformation. And in some models, R parity is assumed to be conserved, which means that the lightest supersymmetric particle, which is R parity -1, cannot decay. Because it's the lightest supersymmetric particle, it will only be able to decay into the standard model particles, which has R parity +1. So R parity would not be conserved in the decay of the lightest supersymmetric particle. But we have to take a closer look if we impose supersymmetry on the standard model. First of all, in the standard model, we only know 1 Higgs doublet. But if we impose supersymmetry, we need to consider 2 Higgs doublets. Because just copy this part of the standard model Lagrangian. The The second term is not allowed by supersymmetry. This term would actually break supersymmetry. So we have to consider two doublets of Higgs's in the minimal supersymmetric standard model. This means 8 degrees of freedom. 3 of these degrees of freedom are absorbed by the masses of the W plus W minus of the Z boson, which means we have 5 additional remaining degrees of freedom, corresponding to 5 massive Higgs bosons. In the super part of the model, this would be considered to be 8 degrees of freedom for the Higgs zeros. 4 of these degrees of freedom are charged, 4 of them are neutral. This will become important at a later point. The second part where you have to have a closer look are the quarks, fermions in general. Fermions have 2 degrees of freedom, and each of these degrees of freedom gets a superpart. You can think of the 2 degrees of freedom as states with positive and negative chirality, which means basically left and right-handed quarks and leptons. And this means that we also have 2 degrees of freedom on the SUSY side. These have spin 0, which means that we have 2 different ups quarks and also 2 different versions of the superpartners of the electron. This will also be an important part of the model building later. And the final part where we have to look a little bit closer are the gauge bosons. So each of the gauge bosons has 2 degrees of freedom. Also the massive ones, because the degrees of freedom that the W and the Z boson get in addition because of their mass are already absorbed in the Higgs zeros. Which means that each of the superpartners of the standard model gauge bosons has exactly 2 degrees of freedom. They are fermions, so this adds up very nicely.
Matthias, just a question, please. And the Kadrigo-Kobayashi scala, which is present for the lower line works, is also present for the sector of the partners.
Yes, you also have mixing between the particles of the superpartners.
And this matrix is the same, or there is some sort of SUSY break which makes a differentiation between these two matrices?
It's really SUSY breaking. I will come to that.
I will come to that. Thank you.
Okay, so we got this. So far I was talking about unbroken SUSY, which, as I said, would mean that the superpartners have the same mass as the standard model particles that we know. But we do not know a charged scalar particle with a mass of 500 keV very roughly, which means that we do not know the superpartner of the electron. And if it had the same mass as the electron, we would have discovered it by now, which means supersymmetry has to be broken. Another problem that you have with unbroken supersymmetry is that in any case, the vacuum expectation value of the Higgs doublets is 0, which means you cannot have electroweak symmetry breaking in an unbroken supersymmetric model. So both the observation that we have no evidence for a scalar with a mass of 500 keV and the observation that the W and Z bosons have mass are hints that supersymmetry, if it exists, must be broken. You can imagine it, you can figure it like this filler crab. So on the one side of the crab you have the standard model with a very small claw, low masses. On the other side of the crab you have the superpartners, which must have very high masses, because if they had low masses we would have discovered them by now. So in general we know SUSY is broken, but we do not know how SUSY is broken. We have no idea about the SUSY breaking mechanism. And typically what we do in high energy physics is then parameterize our ignorance of the SUSY breaking mechanism. So we have to introduce an effective Lagrangian density at the experimental scale, which describes all the effect of SUSY breaking without assuming a particular mechanism of SUSY breaking. And this leads to the minimal supersymmetric standard model of the MSSM. So in addition to the supersymmetrized standard model Lagrangian, you get these self-SUSY breaking terms. You have to sum over the gauge indices and also over the family indices. So looping over 6 quarks, 3 charged leptons, and 3 neutral leptons. So the parameters that we actually get are mass terms for the gauginos, mass parameters and mixing angles for the quarks, leptons, and also some additional Yukawa-like couplings. I have a famous diagram describing these, one of my latest ones. So in total we end up with 124 additional parameters, which we need to describe the effects of SUSY breaking at the experimental scale. So let me now quickly talk about mixing in the MSSM. So the first part where mixing is very important are the neutralinos. What are the neutralinos? The neutralinos are the partners of the gauge bosons that we have in the standard model, as well as the neutral Higgs bosons in the standard model. So basically, all these particles mix due to the electric symmetry breaking to form different mass eigenstates. The mixing is described by this mixing matrix, which we can diagonalize by imposing a Neutrino mixing matrix, and then we end up with the mass eigenstates. So we have 4 different mass eigenstates for the neutrinos, corresponding to the different mixtures of the superpartners of the Vino, the neutrino, and the 2 neutral mixinos that we have in the MSSM. And just to know that the mass eigenstates are usually ordered by their mass. So the neutrino 1 is the lightest one, the neutrino 4 is the heaviest one. And the neutrino 1, if it is a light supersymmetric particle, is a very good candidate for dark matter. This is one of the great benefits of supersymmetry. That if the light supersymmetric particle is stable, and if it is only weakly interacting as a particle, then it is dark matter. The same basically occurs if you look at the charginos, which are the mass eigenstates of the superpartners of the charged gauge bosons and the charged Higgs bosons. So I have the chargino 1 and chargino 2 corresponding to a different mixture of the W and the charged Higgs bosons. And now, to your question, mixing also occurs in this fermion sector. So we have potential mixing between the families, so a up squark would mix with a down squark and so on. And the second very important part is, as I told you, we have 2 different superpartners for the up quark, one left-handed and one right-handed. Also, these can mix in the MSSM. So these are the Feynman diagrams that are responsible for the mixing between right and left-handed eigenstates. And once again, we have a mixing matrix. You get mass eigenstates called stop 1 and stop 2, for instance, if you apply the mixing matrix to the gauge eigenstates. The amount of mixing between right and left-handed fermions is then usually determined by the Yukawa couplings and also the Yukawa-like couplings that you add in the supersymmetry breaking part of the Lagrange. So let me summarize the MSSM. Take the standard model in exactly one supersymmetry operation, which means that each degree of freedom in the standard model gets one superpartner. We do need 2 Higgs doublets in order to not break supersymmetry in a not wanted or anomalous way. The particle content of the standard model extended by its minimal supersymmetric extension is listed here. So we have 2 degrees of freedom for the gluon corresponding to 2 degrees of freedom for gluinos. We have the so-called squarks, sleptons, neutrinos, and charginos, as I just showed. And as I said, in the unconstrained version of the MSSM, we have 124 free parameters. And this is clearly too much. So just to give you an impression, if we want to do some phenomenology with this and then search for supersymmetry at colliders, we typically have to consider all the parameters in the model. And we typically put our data in histograms. If we take an 8-dimensional model and 100 mils per dimension, this would already consume 2.5 gigabytes of RAM. So just technically, 124 parameters is way too many for us. So we have to find some ways to simplify these models. And the first step in simplifying the MSSM is just taking all the parameters that would introduce a very large mixing and also catastrophic CT violation, like complex phases in the mixing matrices, and set these to 0. So this is a step which is very well motivated by the observations that we have. We know roughly the amount of CT violation that we have, and if the parameters that we set to 0 in the simplified model were too large, these observations would be described by the model. In addition, we sometimes assume a unification of some of these mass parameters. So this is really something which is done for simplifying reasons, like unifying the squark mass parameters in some state. If we do not have this unification, we end up with 24 or 18 parameters, 9 parameters for the squark masses, 6 parameters for the slepton masses, 3 mass parameters for the gauginos, and then these additional trilinear couplings and some parameters in the Higgs sector. So this is already much better than the MSSM. We only have 24 parameters instead of 124. But sometimes even this is too much, and we have to go to even simpler models. And one of the even simpler models, actually the simplest model that is typically considered, is the constrained MSSM or CMSSM. Sometimes also called the minimal superconductivity model. In this model, we assume that all these soft-fuzzy breaking parameters unify at a very high energy scale. So this plot shows the running of the standard model gauge couplings as a function of the energy scale. And in supersymmetric models, they unify at a very high energy scale. And what we do to further simplify the phenomenological MSSM is to impose these unification relations at this high energy scale. Which means that in the CMSSM you end up with 4 continuous and 1 discrete parameters. And this is something we can handle very well with our machine. There are also other models, like gauge-mediated supersymmetric breaking models, where we introduce additional messenger fields that mediate the SUSY breaking between a non-accessible sector and the MSSM sector. Also, these GNSV models are usually defined at a very high energy scale, and then the effects of SUSY breaking are evolved down to the experimental available scales. Another model are anomaly-mediated supersymmetric breaking models, where we introduce extra dimensions, and then we assume that SUSY breaking happens in one of these extra dimensions and is confined to this dimension. Which means there is no direct SUSY breaking in the world we are living in, but only in one additional dimension, that the MSSM particles that we can produce in our laboratories cannot access. So the MSSM particles are confined to the known dimensions, SUSY breaking is confined to the extra dimensions, and then you have to have some mechanism mediating SUSY breaking from these extra dimensions to the known dimensions. And typically in AMSV models this can happen by gauge interactions and also by supergravity. And for all of these models, again, typically you have a minimal version where you assume some unification of parameters at a very high energy scale, simply for the reason to reduce the numbers of free parameters in that model. The final thing I want to say about SUSY models is that actually most of the popular models that we have derive from the PMSSM. So also the AMSV and GMSV models, and as I showed you the CMSSM, any of these models corresponds to a given set, a certain set of PMSSM parameters. Which means that it is always possible to describe any of these simplified models in terms of the PMSSM parameters. This is quite important. For instance, for doing calculations of the mass spectrum, the decays, and cross-sections at the end.
So Matthias, does this model include the gravity-mediated model, or gravity-mediated is completely outside the scenario represented?
It depends on the scenario. So in the CMSSM, for instance, it's just an effective model. You can do calculations in the CMSSM without assuming any particularities about SUSY breaking.
I see.
Typically, the CMSSM corresponds to the Supra model, where you have SUSY breaking mediated via Supra. But since I'm an experimentalist, the technicalities of SUSY breaking are not very interesting for us in the first place. But you just want to find effective models describing the phenomenology of SUSY and the experimental thing. So I'm not going to talk a lot about SUSY. Okay, so actually this concludes the first part of my talk. I've introduced now the most popular models that we have in the experimental structures for supersymmetry. And now we need some tools to do calculations in these models. So for a given point in the CMSSM parameter space, for instance, we want to know, is there any chance that we can discover it, for instance, at LHC? And for this we have to know the masses of the SUSY particles, and the mixings of the SUSY particles, the decays of the SUSY particles, everything in the experimental scale. And for this we have tools. So here's a set of questions that we want to answer before we start searching for supersymmetry. As I said, what are the masses, what is the mixing, what are the decays? One of the more important questions is, does this model actually present us with a WIMP LSP? So does this model present us with a canonical finite matter? If it doesn't, we might have a problem. And to answer all these questions, as I said, we have a list of tools. I will just very briefly go to the most popular tools now. You can find some more information on the respective web pages. But there's a set of spectrum calculators that we typically use. So the spectrum calculators calculate the masses of the supersymmetric particles at the experimental stage. Okay. So we have Sveno, South-SUSY, Suspect, Isosupra, and Phoenix is the most popular of these. So you have the free choice. You can use any of these. There are small differences between the calculators, particularly when it comes to higher order corrections. But you can find all the details in the respective documentation. Then we have decay calculators. So once we have calculated the mass spectrum of the SUSY partners, we want to know how do they decay. And for this we have decay calculators. Sveno, in addition to the mass spectrum, also calculates decays. But then we have programs like HDK and SDK, which also do this. We want to know the cross-sections at the LHC at the moment. For this we have Prospino and NLL fast. There are some flavor observables which I will talk about in a minute. You can use SuperISO to calculate supersymmetric corrections to observables in flavor physics. Then, as I mentioned, we have dark matter, so we want to know some astroparticle and cosmological properties of the supersymmetric model that we study. And for this we have, for example, dark soothing omegas. However, it doesn't matter which of these programs you use, the first step is always to calculate the mass spectrum. So the first thing you do is you run a spectrum calculator on the given model. And then you pass the output of that spectrum calculator to the remaining programs. And the communication between these programs is done via the SLHA file format, Susi de Susche part. You can find the documentation of the SLHA here. I have some examples in the following just to introduce this very briefly. An SLHA file consists of individual blocks, and each block has a name, and then typically a set of one or more attributes. And via these attributes you can set the characteristics of the models. Just to show you how this looks like. Okay, you can see the important parts. This is an input file for a spectrum calculator written in the SLHA file format. So the first thing you do is you define a model, and you define some standard model inputs. Blocks and the attributes. And you have the model parameters in this block minpar, and usually some calculated specific settings. Put this into your spectrum calculator, and it calculates the mass spectrum for you. This is the output of the soft conferences. There's this additional block mass, and here you have listed all the masses of the superparticles. Also some nice documentation. And then you can do further things like calculating the decays. Just to mention, the mass calculators also give you the mixing matrices and here also the corresponding set of MSSM parameters. So if you start with a CMSSM model, put it into your spectrum calculator, you also get the corresponding set of MSSM parameters.
In this case, Matthias, you are talking about reducing the number of parameters because you have CMSSM. Yeah. So it's no longer 124.
Sorry?
It's no longer 100.
No.
Around how many parameters?
So the CMSSM you have 5 parameters.
Just 5 parameters.
Exactly.
Tangent beta is there.
Sorry?
Tangent beta is there.
Tangent beta is there. Yes. That is one of the parameters from the sector that more or less almost. Back here. You have the CMSSM parameters here, 0 and 1/2. This is tangent beta, sine u, and sine u. Yeah, so just as I said, each set of parameters for the CMSSM corresponds to a set of parameters in the MSSM and these are the MSSM. And you can pass it to a decay calculator, and the output looks like this. We have a list of decaying particles. This is the particle data ID of the decaying particle. Then you have a collection of decay widths and the selection of particles that the given particle decays. So how to read this? This is the particle data ID of the charge number 1, and this is the branching fraction for the decay of the charge number 1 into a Selleck LA's neutrino and an electron. You can go through the whole list of decays and know everything about the decays and the characteristics of the system. You can also do cross-section calculations. Just very briefly talk about this. This is an example about the Prospino cross-section calculator. It takes one of the output files of SoftSUSE as an input, then you run the program over it, and all you get out is a collection of numbers, and one of these numbers is the cross-section of the LHC files. There's actually a lot of things that you can adjust when you do the cross-section calculations, like specifying the processes, specifying the mass of the particles, stuff like this. I'm not going to talk about the details. I just wanted to show you, give you an impression of how this looks like.
Can you also change the parameters of the detector?
For the cross-section calculations, this is not important, because the cross-section just really calculates the theoretical cross-section without any corrections given by the detectors. If you want to include the detector effects like resolution and acceptance, you have to use a detector simulation. I'm not going to talk about detector simulation here, but if you're interested, we can talk about it later.
You can do detector simulation using bar graph. You can calculate all these things and then you can simulate detector, all the chain.
Yeah.
Using, for instance, a card with CMS or Aula. as MATLAB, you can use to overlay.
I think there is also Delphis available for this. If you're not in one of the experimental collaborations, you can also use Delphis detector cards, which specify the characteristics of Atlas and CMS. You can take a model and put it.
You can always read the swoosh form.
Sorry?
You can always read the swoosh form. And then you see the
So I think this is all of the examples that I have for the tools that we typically use. And the third part of my talk, I'm going to talk about the observables. So what can we measure that is actually sensitive to supersymmetry? So as I have told you, there is no direct evidence for supersymmetry so far. But we have a lot of measurements in the standard model. And in some supersymmetric models, there are corrections to these observables, mainly via loop effects, correction of the X-mass here, which might be detected there. So we can make precision measurements of things like flavor observables, and if we detect a significant deviation with respect to the standard model prediction for this observable, this may provide us with hints on the existence of supersymmetry. But usually these loop corrections are very small, and the higher the mass of the superpartners gets, the smaller these loop corrections get. So you want to look very closely in order not to miss supersymmetry if you have only these low energy observables. So they are called low energy observables because they are typically recorded at an energy scale which is way below the NHC energy scale. And also way below the mass scale of the supersymmetric particles. So if you do not want to miss supersymmetry, like you might have missed the game move, some branch here. What are the observables in flavor physics that we have? So there are a lot of observables in the sector of B physics and also K physics. For instance, if you look at the decay of the B sub S meson into two leptons, in particular B sub S into muons, in the standard model, this is one of the dominant contributions to this decay. If you consider a supersymmetric model, you can replace two of the standard model particles by additional particles that you only have in the MSSM, and this alters the prediction of the branching ratio for the B sub S to mu. I think we just had a measurement of B sub S to mu by LHCb, which was actually in quite good agreement with the standard model, unfortunately. But there are also other observables, like the decay of a B quark into an S quark and a photon. If you look at the standard model, this can happen via the radiation of a W boson, which is recaptured by the quark later. So the quark can change its flavor, and in addition, as a tablet of a photon. If you consider supersymmetric models, then once again exchange the standard model particles in the loop with supersymmetric particles, and this also alters the prediction of these observables. One of the most interesting observables maybe is the anomalous magnetic moment of the muon, which in the standard model is maybe written in these Feynman diagrams. But again, in supersymmetric models, you can replace the standard model particles in the loops by superpartners, and you get corrections to this observable. We also have precision measurements at the electroweak scale, mainly from lab at the SLC.
Matthias, could you come back to the previous slide, please? No, just is a quick question, maybe it's very simple for you. My question is, maybe, I mean, not only SUSY is the physics beyond the standard model. Sometimes we have perhaps contributions coming from Z0 primes, W plus primes, and at the level of these high precision measurements, could you distinguish whether your contribution is coming from the SUSY sector or from this extra dimensional sector?
If you take only one observable, probably not. Because, so if you look at this contribution here, you have the charge sticks and some additional exposons here. So no superpartners actually. There are contributions from the superpartners as well. But if you measure a significant deviation from the standard model, just in this decay from the B sub S to mu, this might be just some model where you have two examples. No supersymmetry at all. If you put all the observables together, the picture might change. We'll come to that in a second. Okay, so back to the precision measurements at the Z scale. So we know quite precisely the mass of the Z boson, the W boson, the decay width. We have a lot of measurements of hadronic cross sections at E plus E minus colliders, and also a lot of forward-backward asymmetries and left-right asymmetries at these outliers. And all of these observables might receive small corrections from supersymmetry. Once again, the problem is that the corrections are typically very, very small. So we have to look very closely in order to find a significant deviation from the standard model in these observables. And also coming back to the other models magnetic moment of the muon, some of the observables are not quite undisputed, I would say. So here's a measurement of the deviation of this magnetic moment from the muon from the standard model. So the deviation of the measurement from the standard model is 28.7 plus or minus 8.2 times 10 to the minus 10. This is significant already. The deviation is more than 3 sigma, which is usually considered as a hint that there is something going on. The problem with this observable is that the standard model prediction for a mu is not quite undisputed. The problem is that the standard model prediction consists of 3 parts corresponding to the 3 gauge iterations that we have in the standard model. And we can calculate the quantum electrodynamic and also the weak contribution, but we cannot calculate the hadronic contribution to this observable, simply because it is measured at an energy scale where QCD is not pathological. So we have to measure it. And the way that this is usually done is you measure the hadronic cross-section at a plus or minus collider at the respective energy scale, and then you try to extrapolate from this to this, because you can see the vertex is actually the same. We have some hadronic interaction going in a loop here, and if you cut the loop into 1/2, you basically end up with the production of hadrons at the plus or minus collider. There are also other ways to estimate the hadronic contribution to the magnetic moment of the muon. And depending on which measurement you use to calculate this hadronic contribution, you get very different answers. So the prediction for this observable, the standard model prediction for this observable, is not quite unambiguous. There are difficulties here on the theory side. So what we usually want is we want to have more explicit observables from which we can definitely tell the existence of supersymmetry or something similar.
Matthias, presently the stages of this search for us in research for these contributions, if you look at the tau magnetic moment, is it very complicated from the experimental point of view to have the measurement of the tau magnetic moment?
Yes, I think this, I'm not an expert in this area, but the idea of measuring the magnetic moment of a muon is to measure its precision in a magnetic field. It means it has to live a certain amount of time in order to perform this measurement. And tau decay is much faster, so it's very problematic to build a tau accelerator. We are struggling with building a muon collider or muon accelerator and tau's no way. Okay. So there are observables which might tell us about the existence of supersymmetry. For instance, the existence of dark matter. To mention this, Carsten mentioned it in his talk this Tuesday. So we know that a large fraction of the mass in the universe, of the energy in the universe, is made up by dark matter. And the standard model does not predict anything for dark matter. So according to the standard model, dark matter should be zero. As I said, supersymmetry provides a candidate for dark matter, so according to supersymmetry, dark matter may be there. One of the questions then is how much dark matter predicts a supersymmetric model. We can use our calculators to do this. And we can then ask, what other predictions does the supersymmetric model make about the experiments in which we try to detect dark matter? So far we only know that dark matter is there, but we haven't detected it directly yet on the Earth. With experiments based on the Earth and also space around the Earth. There are different experiments trying to do this. For instance, direct detection experiments, I have a slide on this in the following, but also indirect measurements where we measure the fluxes of standard model particles in space. And one of the important things that a supersymmetric model should do is predict the observables for these experiments. So for instance, if we go to the direct detection experiments, the idea is basically you put a large amount of matter somewhere on Earth, and then you wait for dark matter particles to pass by and interact with the nucleus. You can measure the interaction of dark matter particles with the nuclei, for instance by measuring the report energy or measuring phonons. A supersymmetric model should be able to predict the rate that these interactions appear. So if we measure nothing for a very long time, we can rule out a certain set of SUSY models. If we measure something, we can test our supersymmetric models by comparing the prediction of SUSY models with the actual measurements. There are a lot of experiments trying to detect dark matter directly. The results are shown in this plot, where you have the mass of the dark matter particle versus the cross-section for the dark matter particle nucleon interaction. And the problem with these measurements is that when we have 5, 6 experiments, 3 of these, maybe 4, one hasn't decided yet, they claim the detection of a signal. And the signal region that they claim to detect is shown in the color fields here. As you can see, the different claims for a signal detection are not in agreement with each other. So the CREST experiment predicts something that is not in agreement with the prediction of CMS, for instance. Also, one of the simplest models in supersymmetry that we have, the CMSSM, is in quite a bit disagreement with the measurements that the signals that these experiments get. Also, other experiments, as I say, like Xenon 100, they do not yet claim the detection of any signal. They have excluded all the phase space up here. So we are not quite sure how to interpret these direct detection.
In that graph, I will take account the last March results from the Planck.
Yeah.
This is the update, the most updated results we have.
Yeah, but they only predict the amount of dark matter. They do not say anything about the mass of the dark matter particle or the cross-section for these direct detection experiments.
Just the amount.
Just the amount. And there's one other experiment that I would like to mention here. This is an experiment for the indirect detection of dark matter. The basic process that this experiment is trying to measure is the annihilation of 2 dark matter particles in space into standard model particles like electrons and positons. So you have a giant spectrometer at the International Space Station, and all the spectrometer does, there's a lot more, but one of the most important things the spectrometer does is measuring the flux of electrons and positons. What you see in this plot as a function of the positron and electron energy is the fraction of positons in the total flux. So we count how many electrons were there, how many positons were there, and we calculate the fraction of positons divided by positons with electrons. And they observe an excess of positons in this energy region. They have about 400,000 positons too much. This is evidence for new physics already, but it is, again, not enough to say, well, it's supersymmetric dark matter, it is some other sort of dark matter. We have to wait a little bit longer for more results, particularly in the high energy section of this experiment. If the excess is stable over time, and also in the high energy region, this is quite a clear hint on the existence of some weakly interacting.
But this result excludes axions, for example.
I'm not sure about that.
It could be axions.
I think it might be, but so this is one of the reasons why we have to wait for the measurement in the high energy region. If it was axions, I think you wouldn't expect an excess in the high energy region, but I'm not quite sure. Okay, so if we take all this together, we have a lot of observables, but not a lot of sensitivity to supersymmetry. So one of the most powerful things that we can do is looking for supersymmetry at particle colliders. This has been in the past at the Large Electron Positron Collider, also at the Tevatron, and it has recently begun at the Large Hadron Collider, where we will once again start to search for supersymmetry in 2015. Here's an image of the Large Hadron Collider. It's at CERN in Geneva. You have a 27-kilometer circumference collider in roughly 100 meters beneath the Earth. For the SUSY searchers, the most important thing that this collider does is it accelerates protons to a mass of 3.5, energy of 3.5 tera electron volts, and then we collide the protons at the major experiments that we have, ALICE, ATLAS, LHCb, and also CMS. And we could find supersymmetry at the Large Hadron Collider simply by directly producing the supersymmetric particles. Here are some Feynman diagrams. Of course, we have protons, so strong production of SUSY particles would be the most interesting thing. You have a gluon fusion, and the gluon is split into a squark and an anti-squark. can also scatter a gluon of a quark and one of the other protons and produce all the combinations of squarks and neutrinos in these scenarios. Another very interesting part would be the electroweak production of supersymmetric particles. You could have the exchange of the Z on a photon and produce leptons, neutrinos, and I don't have the family diagrams for this, but you could also directly produce neutrinos and charge ions. And as I say, there are many additional diagrams, so this is just a very incomplete snapshot of what might happen at the LHC. Now we produce superpartners at the LHC, and then we have to look at the what happens to these superpartners at the LHC. We consider a typical SUSY scenario. The decay width of a typical superpartner is between 1 and 50 GeV, which means that the average lifetime is at the order of 10 to the minus 25 seconds. It means that even if this particle would turn at the speed of light through the detectors, it would only cover a distance of 10 to the minus 60 meters. So, on the experimental scales that we have at the Large Hadron Collider, superpartners decay instantly. And then all of them do, except for the lightest supersymmetric particle if it is stable. So, for instance, you had the direct production of a neutrino 2 and a charge nu 1, the W boson. They would instantly decay, for instance, into a lepton and a lepton. And then the lepton, once again, would instantly decay into a lepton and the LSP. So, the only thing that would come out of this collision, this example, are 3 charged leptons, 1 neutrino, and 2 LSPs. And the same thing for the color production, where the decay chains can typically be much longer. So, what we are doing is, we build experiments around the interaction points at the LHC. So, this is the CMS detector and the ATLAS detector. These are the 2 experiments that mainly drive the search for supersymmetry at the LHC. We have the V-pipe serial, so protons come in here and here, and at the very center of the detector there comes the collision. So the very center of this detector, the superpartners will be created, decay instantly, and then we produce the detectors to discover the decay products of the superpartners. The structure of such an experiment is typically always the same. So here's a cross-section of the ATLAS experiment. So you can imagine the protons coming into the plane of the screen and coming out of the plane of the screen. They've collided right here in the center. And then the detectors consist of a tracking detector very close to the interaction point. Then we have an electromagnetic calorimeter, hadronic calorimeter, and a muon spectrometer at the very outermost part of the detectors. And then we can combine the information from different sub-detectors to determine the nature of the particles that emerge from one of these interactions. Just to explain a few examples, if an electron was coming out of the part interaction, we would have a track in the tracking detector and an electromagnetic shower in the electromagnetic calorimeter. If on the other hand we had a muon coming out of the part interaction, we would have a track in the tracking detector, just like for the electron. But since the muon is much heavier than the electron, there is close to zero deposition of energy in the electromagnetic calorimeter and also in the hadronic calorimeter. But once again, we would have a track in the muon spectrometer. So we can distinguish between electrons and muons just by combining the different informations from the different parts of the detectors. And we can also do this for other particles like photons, neutrons, protons, you name them. There are a lot of different signal regions where we are looking for supersymmetry. This is one of the slides from one of my other slides, but I guess you could easily extrapolate it to CMS as well. They are looking in very similar regions, depending on the models that we are looking for. So prompt means that superpartners decay simply, as I showed you slide before. You can look at models where R parity is violated, but also at models where R parity is conserved. R parity conservation, as I said, is interesting for us because only if R parity is conserved, SUSY provides us with a good parameter candidate. And you can look in a lot of different final states. Just put some examples on this slide. But we also have long list scenarios where the superpartners do not decay instantly, but due to small mass differences between a supersymmetric particle and the next slightest supersymmetric particle which it can decay, they may acquire quite significant lifetimes. And we also try to cover these scenarios and these long lived searches.
long-lived enough, you can say, around the QCD time decay, or even
Much
less?
longer.
Much lower.
So much longer.
Much longer.
One of the searches that we have is that we are looking for disappearing tracks in the inner detector. So you would have, for instance, in this scenario, you would have a chargino which comes out of the interaction, and might decay somewhere in the tracking detector into a neutralino and a pion typically. And then you would have a high ET track somewhere here, which would end quite probably somewhere in the tracking detector. You wouldn't escape the LSP because it is on the weakly interaction. You cannot measure the LSP in the detector. And the pion would have way too low defensive momentum to be detected at all. So all you will see is a track disappearing somewhere in the detector. This is one of the most striking signatures that we take at the moment. Now I'm talking a bit about statistics. So after doing some measurement, how do we decide if we found SUSY or not? Because all we can measure are standard model particles, in the standard scenarios at least. And standard model particles are also produced at the LHC via standard model interactions. So we have a background. Background are standard model processes that mimic the same signature as the supersymmetric processes that we have. And supersymmetry would show up as a significant excess in the number of observed events compared to the standard model. So the basic formula, the statistical distribution that we use is a Poisson distribution. Here are some examples. For instance, if in the standard model you would expect something like 30 events, this would be your probability distribution function for the number of observed events. And say standard model expectation is 30 events, you measure 50 events. And you can use this distribution to calculate the probability to observe 50 events given that the standard model is the actual true underlying field. If you compare this to an arbitrary supersymmetric model where the expectation value is actually 50, you will see that the probability to observe 50 events in the supersymmetric model is much higher than in the standard model alone. And if the difference between these two probabilities is large enough, then we will speak of a discovery. Not necessarily of supersymmetry, but we would speak of a measurement of significant discrepancy against the standard model. The problem is usually that even at the LHC, in the most popular models that are not yet ruled out, is that the MSSM will show up as a very, very small deviation against the standard model. So you can think of two dice, one is the standard model dice, one is an MSSM dice, and you try to find out if it is an honest dice. And this dice has 12 sides, so you have to throw it quite often in order to find out if each of the 12 numbers appears with the same probability. And usually, the MSSM would be just a very small defect on this dice, so you have to roll the dice even more often to find significant discrepancy. Just to show one example of a SUSY search at the LHC. This is a typical CMSSM mass spectrum. Typical is always a bit, isn't quite the right word when talking about supersymmetry, because there are all the kinds of different models. But, well, let's just say it is a typical mass spectrum in the CMSSM. And you can see is that all the colored particles are very heavy. These are the right chiral squarks, the gluino, and the left chiral squarks. Then the superpartners of the leptons are a little bit lighter. The right chiral ones, the left chiral ones. And then somewhere in between you have the neutralinos and the charginos, with usually the neutralino one being the lightest supersymmetric particle. And if we take this mass spectrum and look at the SUSY production cross-sections at the LHC, you can see that actually the production of the color charged particles dominates the production of all the other particles. So in the mass spectrum, colored particles have a mass of very roughly 1 TeV, so this corresponds to cross-sections at about 10 to the minus 1 kiloton. If you take the neutrinos, the mass of about 300 or 400 TeV, look at the cross-sections here, it's very roughly 10 to the minus 2 kiloton. So the production cross-section for colored particles is usually very high in the CMSSM compared to the production cross-section for other particles. And the dominant decays in the CMSSM listed here. So if you produce a neutrino, it decays in 100% of the cases into a squark and a quark. The squarks can decay into charginos and neutralinos and a quark. Neutralinos decay typically into the star pair or an LSP and the Higgs boson or Z boson. And the charginos typically decay into a W boson and the LSP or in a star and a neutrino, but they could also decay into lighter charginos and neutralinos. Typically what you would have in the final state then is two light supersymmetric particles, but you cannot detect in the detector, so you have missing energy. And you have a good chance to have some jets in the final state, because the production cross-sections for squarks and neutrinos is very high. And well, if you have a squark or a neutrino in the initial state, you always have a quark forms a jet in the detector in the final state. So we have a good chance of finding supersymmetry in this E and this M by looking into final states with jets. And also in some cases you have one or more leptons, charged leptons in the final state. Here's what a typical SUSY event in the CMSSM would look like. Once again, typical is a should be very careful with the word typical. Here you would have the pair production of two neutrinos decaying each into two quarks and some chargino. Chargino decaying into a neutrino and W boson, neutrino decaying into a Z boson and the LSP. Both sides the same, but the topologies will also look very different on both sides. So in this event, we would have at least 4 jets, and then whatever the W and Z bosons became. Neutrinos, leptons, or just additional jets. So this is one of the other searches for supersymmetry, where we are looking for SUSY in final states with only 2 to 6 jets. So the target topologies for this search are much simpler. Target the pair production of squarks, which decay directly into the LSP in the quark. So in this example, you would only have 2 jets in the final state. You could also have pair production of squarks, but the squarks decay near the next to lightest neutrino into a Z boson and an LSP. So you could have up to 6 jets. We have a lot of different signal regions, each optimized for a different region of the parameter phase space, and we are just counting the number of events in these regions. This is all that we do. Here are the results of the search. This is a distribution of the effective mass, which is one of the observables that we build from the measurements that we do in the experiment. In black, you see the data points, and the color histograms is the standard model expectation. Maybe it's best to look at this plot at the bottom, which just shows the ratio of the data divided by the standard model expectation. The ratio is very close to 1 in all of the bins, which means that we have no significant excess. And we can use this information to exclude certain parts of the CMSSM parameter space. And we exclude everything that lies beyond this line. So everything below this line is excluded just by this one measurement. If you move above the line, the production cross-section and the acceptance at the experiment will be too small, so the deviation that we would actually expect is too small to be detected at the moment. So what we typically would do is measure for a longer time and get more events and the small deviation and the larger deviation. Or we could also increase the center of mass energy, which would increase the production cross-section. Okay, I think that is everything I have on the observables. So now I have the final part of my talk, which is about global fits of SUSY models. This is about putting everything together. So we take all the observables that we have: flux, dark matter density, the direct detection, direct detection, the measurements from the LHC, and also the flavor measurements. Put all of it together. And then we add some really cool algorithm. Now we get out as a complete analysis of the supersymmetric model that we put into this fit. And the question that we try to answer with this procedure is: how well does a given model describe all the available measurements? Can we rule that model out? And if not, what are the other predictions that this model makes that we might be able to test? And then we can test them and rule the model out afterwards. The collaboration I'm working in is the Fitino collaboration, which is one of the collaborations trying to tackle this problem. So what we are doing is we start with an input file where we have a set of observables and uncertainties, and also a set of parameter start values. And then we use the tools that I was talking about earlier to calculate masses, low energy observables, rates at the LHC, everything at the experimental scale. So we calculate the observables, and then we calculate the chi-square, which basically is a comparison of all the predictions that this model makes with all the observables that we have. And based on this chi-square, we jump to a new point in the model parameter space and start over again. So we are testing a lot of points in a given model. We are varying the parameter values of a given model and trying to find out what set of parameters describes all the available measurements in the best possible way. Just some details on the chi-square calculation. So, as I showed on the previous slide, the chi-square is calculated by subtracting the measurement from the prediction at a given point, divided by the uncertainty. Just a very simple example of how the chi-square would look like in a simple model with only two observables. And you know these two measurements, I have shown them before, and say that some point in this n parameter space predicts a magnetic moment of 23.7 times 10 to the minus 10 and a diameter density of 12.51. Final chi-square would be 1.49. I will come back to the chi-square in a second. Now we have two related questions. One is, what is the best set of parameters, which means what is the set of parameters with the smallest chi-square in a given model, providing the best agreement between predictions and observables, and how good is the actual agreement between these predictions and the measurements. So 1.49, is it good? Is it bad? I'll try to answer that question in a second. First thing we have to do is we have to find this best fit point. We have to find the set of parameters that describes all the measurements best. And the easiest way to think about how we do it is think about the parameter space as a landscape, and the chi-square is the height, the altitude in this landscape. And all we are trying to do is to find the lowest value in this landscape. But we do not want to get stuck in the second or the third lowest value. We want to find the lowest value. And it is problematic because you can think of us walking around in this landscape basically blind. We can only evaluate the chi-square, measure the height, at the point in the parameter space where we are currently standing. We do not know the value of the chi-square one step ahead and also not one step behind it. We can always make a step, write down our coordinates at the chi-square, and when blindfolded again, make another step, do the same thing, and so on. And there are several algorithms that steer this walking around in the parameter space in a very smart way. The preferred way for the moment is a Markov chain Monte Carlo. I will explain it in a second. Just for completeness, to mention the other algorithms that we have, like simulated competing gradient-based algorithms. We are exploring the possibility to use particle swarms, and at some point also simple sampling, which is just moving around in the landscape on a fixed grid, which is not a very smart thing. So how does the Markov chain Monte Carlo work? Basically, we started at some point in the parameter space. This might be randomly chosen, but we can also use tree-level calculations to calculate back from the measured values of the observables to the parameter values. At higher order calculations, this usually doesn't work because the relations between parameters and observables are not invertible at that level. So we have our starting point, then we evaluate the chi-square at that point, and then we jump to a new point, and we evaluate the chi-square at the new point. How do we jump to this point? This is done by proposal PDFs. So we take the point in the parameter space we are currently standing, and then we just roll a random number according to some distribution that we can freely choose, and we walk randomly to a new point in the parameter space. And we calculate the chi-square at the new point, and then the key point of this algorithm is to compare the new point to the last accepted point. Calculate the chi-square difference, chi-square at the new point minus chi-square at the old point. If the chi-square at the new point is better than at the old point, we accept it, and we make our next step from this new point. If the chi-square at the new point is higher than the chi-square at the old point, we only accept that point with a certain probability. Why? I will come to that in a second. If we do not accept this point, we just go back to the previous point and throw a new random number, starting at that point again. So why do we accept worse points with a certain probability? The idea of this is that this allows the algorithm to escape from local minimum. So if you look at this chi-square landscape, we have one parameter on the x-axis, one parameter on the y-axis, and the chi-square on the z-axis. And for instance, you can imagine that our algorithm starts somewhere here and very quickly finds this minimum. And in this minimum, it is able to walk around relatively easily to find the true minimum at this point. But in fact, the true minimum is here, at the very center of the time. So in order to get from this minimum to this minimum, we have to cross a potential wall. And the point that if we are stuck at this point, and the random algorithm takes us to this point, the fact that we accept this point with a certain probability allows us to cross this probability wall. And this leads to a very effective sampling of the parameter space. And in the end, we have a collection of points with a chi-square calculated at each point. Due to the algorithm, we have a very good sampling close to the minimum. So this plot shows the chi-square of the points and the number of points with a given chi-square. As you can see, we have a lot of points with a small chi-square, but only a few points with a very high chi-square. And the idea is that with such a sampling, we can very precisely study not only the best fit point, but also the area in the parameter space around that best fit point. Why do we want to do this? First part of the answer is that the minimal chi-square, as you can see from this plot, is not zero. If you just look at this formula, you would expect that, well, if all the observables are predicted by the model in a perfect way, you would expect a chi-square of 0 if the model is the true model. The point is that our measurements are not perfect. So, on average, we expect a certain deviation from the true model's prediction if we compare the measurements to the predictions, simply because our measurements are not perfect. And the second part of the answer to the question why the minimal chi-square is 0 is that usually we want to have an over-constrained fit. What is over-constrained? So if you think about what's in the fit, we have d parameters that we can vary freely, and we have x observables that have measured values. And basically what we are trying to do is solve a set of equations. So for each of the x observables, we have one equation. We have the prediction as a function of the model parameters, and the solution of this prediction is the measurement. So finally, we have x equations and d parameters that we can vary to solve the system of equations. Now, if the number of observables is smaller or equal to the number of parameters, it's always possible to find a good solution. Think about 2 points, trying to fit a straight line through these 2 points. It's always possible. If you had a third point, it might not be possible to fit a straight line through. And the reason why we want to have over-constrained fits is that if the true model in this example was a straight line, we would expect, even if on average there is a certain deviation from the model prediction, we would expect that on average the predictions of the model describe the measurements quite well. Even if we have more measurements than we have parameters that we can adjust. This is about the degrees of freedom of the fit. So the difference between the number of observables and the number of parameters of the tested model is called degrees of freedom of the fit. And we want the degrees of freedom to be a positive number. Then you can perform the fit. You can find our minimal chi-square, which will be different from 0. And then we can ask ourselves, so is it still possible, even if we have more equations than parameters, to find a good solution? If no, we can exclude the model. If yes, we cannot exclude the model. We can look for predictions this model makes and more measurements that we can use to constrain the model. The final answer, the final question that we have to answer is, what is a good solution? And the answer to this question is given by the chi-square distributions. So we look at the minimal value of the chi-square that is found in the fit, and then we ask ourselves, what is the probability to find chi-square as bad or worse as the one that we found? And the probability distributions for chi-squares are described by this formula, only in the case that all the observables that we measure have Gaussian uncertainties. So if all the measurements that we do have Gaussian uncertainties, we can simply find the given chi-square and calculate with this formula the probability that we find a chi-square as bad or worse as the one that we found. And then usually, this probability is called a p-value, and if this p-value is smaller than 5%, consider a model excluded at the 95% confidence level. If it is larger than 5%, well, we have to measure a bit longer. If the uncertainties are not Gaussian, the way that we can still try to find out if the quality of the fit was good or not is to run toy experiments. So what we do is we take the best fit point, we take the predictions at the best fit point, and then we generate a lot of toy experiments for this best fit point. So we throw a lot of times we throw random numbers for predictions, and then for each of the potential experimental results, we run our fit. We get a result with a certain chi-square, and in the end we get a chi-square distribution. And then we can use this chi-square distribution, which will differ from the distribution I showed you on the slide before, and try to find out how probable it is to find a chi-square in the original fit as bad or worse as the one that we found. Calculate the chi-square again, and this will give us the p-value. So in this example, the white plot is the distribution for all the chi-squares from the toys, and the blue plot is the fraction of these points where the chi-square is worse than the one that we found in the original fit, 3.6. So we have 3080 points in 10